In this video, we're going to investigate the fundamental theorem of calculus number 2. When we looked at the fundamental theorem of calculus number 1, we investigated the derivative of the accumulation function, the derivative of some particular integral, and we saw how that worked. And in this video, we're going to go the other way around. We're going to take, in some sense, the integral of a derivative. So let me consider just the integral from a to b, a definite integral from a to b of f of x dx. Now, this had a particular geometric meaning. We saw that that was the area under the curve. And in fact, we had defined what this was. It was kind of a messy thing. We would define it to be this limit of this sum of these little rectangles. We had a whole process for that. But one of the things that came up is that computing integrals from the definition was kind of hard. Even for really simple functions, going the formal way took a lot of effort. So we want to have a tool that allows us to do these, allows us to compute these areas much easier. And fundamental theorem of calculus number 2 is the answer. So how are we going to do this? What I want to begin with is I want to imagine, I've got this little f here, I want you to imagine that you have an antiderivative of it. That is, I want you to imagine that you have some function capital F of x where the derivative of capital F is little f. Now, why is that important? Because if you have such an antiderivative, capital F, then the statement of the fundamental theorem of calculus 2 is that this particular definite integral is just going to be the big F at the value of b minus the big F at the value of a, and that is going to be our fundamental theorem of calculus. So what really is going on here? When I look at this little f, I'm saying, well, look, the lowercase f is the derivative of something. And then what we're saying here is that the integral of the derivative of something is just back at the original level of the function, original level of f of x, except if it's a definite integral and I'm going from a to b, I have to take the quotients, that function capital F at b minus that function capital F at the value of a. So while this theorem is investigating the integral of a derivative, the first fundamental theorem of calculus, it investigated the derivative of an integral. Alright, so let's see how this plays out in the specific example of the definite integral from 1 to 2 of x squared dx. First thing I need to do is find an antiderivative. Well, what about this particular function here, where I'm saying x cubed over 3, and I can verify that the derivative of that, by the power rule, is 3x squared divided by 3, the 3's cancel, and I'm just left with x squared. So that's not so bad. I have this, and that's going to be my antiderivative. Now, what does fundamental theorem of calculus say? It says it's just the antiderivative at the value of 2 minus the antiderivative at the value of 1. And I can compute those. That's 2 cubed over 3 minus 1 cubed over 3. Now, I could give you a different function in a different interval, but as long as you can give me an antiderivative, the fundamental theorem of calculus is going to make computing all of these definite integrals really easy, just a matter of substitution. So the goal of finding antiderivatives, that's really the big challenge when it comes to definite integration. Now, the final point I want to make when I think about the first fundamental theorem of calculus, the second fundamental theorem of calculus, is that there is actually 3 different types of objects, types of mathematical objects that are similar, that have integral signs, that are related, but are all slightly different. For example, if I have the so-called indefinite integral, this is the one where I don't give any limits of integration. Well, the outcome of this, something like x cubed over 3 plus c, this is what we call a family of functions, which is to say, for every value of c, you get a slightly different function. There's a whole family of them. For every c, you get a different function. I can also consider the accumulation function. Those were the subjects of the first fundamental theorem of calculus. And here, the accumulation function, the integral from a up to x of some t squared dt. Well, what's that? That is a function of x. It's not a family of functions, no plus c any longer, but for every value of x, you get an output, you get a number, you get the area. So it's a function. Every input gives you an output. And then finally, for a definite integral, this is what we get out of the fundamental theorem of calculus number 2. This is an integral from a to b where I specify both bounds. And here I actually get a value. This thing is a number. It's just the antiderivative at b, whatever number that is, minus the antiderivative at a, whatever number that is. So as you go through the fundamental theorems of calculus and you're playing around with integrations, always keep clear in your mind. Are you computing a number? Are you computing a function? Or are you computing a family of functions?